Hello and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 7, Lesson 7 on more work with square roots. Now we introduced the idea of a square root in the last lesson and let's review that fundamental idea right away. Finding the square root of a number is the inverse or the opposite of squaring a number, multiplying it by itself, right? So let me just kind of move this out of the way so we can see the entire graphic. If I start with the number 8 and I square it, I get the number 64. On the other hand, if I take the number 64 and I find its square root, I get back to the number 8. All right? So literally, a square root is the opposite or the undoing of a squaring. And we kind of talked about it last time in terms of area, right? If I have a square that's got a side length of 8, it's got an area of 64. And if I have a square with an area of 64, it's got a side length of 8. So one way that one can think about the square root is it's finding the side length of a square that has the area of the number under the square root. Remember, that number is called the radicand, right? The radicand. Now, for today's lesson, we're going to work more with square roots, and we're certainly going to use our calculators just a bit. So make sure to have those available to you. But when possible, make sure to be trying to find the value of the square root in your head. If the number underneath that square root is a relatively small perfect square, all right, then you should find it without using your calculator. Use your calculator to verify, but try to find it just by using your knowledge of the multiplication or times tables. All right, let's take a look at exercise number 1. Without your calculator, find the value of each of the following, justify using a product. All right, so this is just, can you tell me what the square root of 100, the square root of 4, and the square root of 49 are? Why don't you pause the video now and find the value of each of those square roots. All right, each one of these numbers is a perfect square. Each radicand here is a perfect square. So the square root of 100 is equal to 10 because 10 times 10 equals 100. The square root of 4 is equal to 2 because 2 times 2 is equal to 4. The square root of 49 is equal to 7 because 7 times 7 is equal to 49. Now, I mentioned this in the last lesson on square roots, but I really want to hammer it home again. This equal sign means that this thing and this thing are the same number. Literally, the square root of 100 and the number 10 are the same number. Just as I could say 10 is equal to 2 times 5, right? 2 times 5 and 10 are the same thing. I can say that the square root of 100 is equal to 2 times 5. I could say the square root of 100 is equal to 8 plus 2, right? Because both of them are equal to 10. My point is going to be illustrated even better in the next exercise, right? Square roots show up in a lot of different calculations, okay? You'll see them in science all over the place. We'll see them in tons and tons of math applications as we move forward, both in this course and, of course, a lot in future courses. If the result of a square root is a whole number, like the ones we just did, it's best to just evaluate them and then finish off the problem. So let's take a look at what I'm getting at in exercise number 2. Evaluate each of the following by first simplifying the square root. All right, so far all you've done with square roots is basically given me their values, but you haven't done anything with those values. Here, on the other hand, in letter A, I have 5 plus the square root of 16. Well, what is that equal to? What is its value, right? That's what evaluate means. It means to find the value of a mathematical expression. Well, what I could do in this case is I could say, look, I know the square root of 16 is equal to 4, so 5 plus the square root of 16 must be 5 plus 4, and that must be equal to 9. Okay? Now, side note, I would not want you to do this with your calculator, but since we like our calculators and we tend to trust our calculators, if I put 5 plus the square root of 16 into my calculator, right, the exact calculation that I've got up on the board right now, and I hit enter, it tells me the result's 9. All right? So I want you to keep in mind that every time I have a square root, right, even if the number underneath it is not a nice perfect square, it is still, overall, the square root is a number. So what I'd like you to do is try to figure out the values of B and C. First evaluate what the square root is, and then do any other operations that the expression is indicating. Pause the video now. All right, well first, make sure you even understand what this means, right? This literally means 7 times the square root of 25, right? Right? Just like if I had something like this, that would mean 7 times x, right? This means 7 times the square root of 25. But we know what the square root of 25 is. It's equal to 5, right? Because 5 times 5 is 25. So this is just the same as 7 times 5, and that is equal to 35. Now, this one is probably a little bit more obvious maybe than this one. This literally is the square root of 64 divided by 2. In which case, the square root of 64, right, is 8. And 8 divided by 2 is equal to 4. And again, that's it. What I'm trying to get at in this exercise, though, is that the value of the square root, right, is just a number. And when square roots show up in calculations, if we can evaluate what that square root is equal to, we should, right away. And if we can't, because the number underneath the square root is not a perfect square, that's when we bring out our calculator and maybe we use it to do its thing. All right. Now, we're going to kind of segue to a different topic right now that involves square roots, and it's kind of a cool one. Recall first that rational numbers, numbers written as fractions containing integers, have either terminating or repeating decimal representations, all right? So any number that you can write as a fraction, negative or positive, right, where the numerator and denominator are both integers, all right? So they're both integers. Those are called rational numbers, all right? So let's just take a look at exercise number 3. As we know, rational numbers, numbers that can be written as fractions involving integers, have decimals that terminate, i.e. they just end, or start repeating. For each rational number below, use your calculator to write its decimal expansion. Use the repeating decimal bar when needed. All right, just for kicks and grins, let's do the first 2 together and then we'll have you do the last 2 by yourself, just for kicks and grins. So the first one is 2/3, right? So easy enough, right? If I want its decimal representation and I don't know it off the top of my head, which you might with 2/3, I put 2 divided by 3 into my calculator, I get 0.66666. That last one, that 0.7, we'll talk about that in a moment, but I'm going to say that that is that, 0.6 repeated. Now a little side note, the reason that there's a 7 here isn't because it suddenly terminated with a 7. It didn't. It's that the calculator knows that it's 0.6 forever. This is the last decimal it can represent, so it looks at the next one over, that's a 6, and it bumps the 6 that would have been here up to a 7. So the calculator by default has to eventually terminate the decimals because otherwise the screen would have to be kind of infinitely wide. All right, now that's one that repeats. Let's take a look at one that doesn't repeat, that just terminates. So if I do 3/8 or 3 divided by 8 and I hit enter, I just get 0.375, right? There's no repeating decimal bar, right? Unless you want to put a 0 after that and then put a repeating decimal bar over that, and that'd be a little weird. Okay, so there we go. What I'd like you to do is figure out the decimal representation for 5/6 and 1/27, all right? And put the repeating decimal bar wherever you need to, but be careful about that. Pause the video now and go ahead and do this. All right, let's take a look at 5/6. I love the number 5/6. It's kind of got a cool decimal representation. 5/6, enter, right? 0.83. Now, let's talk about this a little bit before we put down the repeated decimal bar, all right? Notice that it's 0.8333333. I would never want to put the bar over the 8 and the 3 because that would imply that my number is actually 0.8383838383, right? We only put the bar over the portion that's repeating, not just over everything, okay? In this case, this is the way I would represent it. 0.83 with the bar above the 3. Now the 1/27th, you don't get any better than this one, right? So 1 divided by 27 is 0.037037037, etc. So this one's kind of cool because we have this sort of repeating pattern, right, of 3 different digits again and again and again. 0.037, 0.037, 0.037, actually it's 0.03703703703. There's not a point that keeps repeating. But then that's that one. Now, I'd like to take a look at some square roots and see what their decimal expansions look like. Now, I want to note that every one of the numbers underneath here are non-perfect squares. Obviously, if I have the square root of 9, the answer there is 3. And that's a rational number because it terminates. Or if I had the square root of 64, that's 8. And that's a rational number because it terminates. So we are only looking at the square roots of non-perfect squares right now. Let's take a look at exercise number 4. Use your calculator to evaluate each of the following square roots. Write out every decimal place your calculator displays. All right, so for instance, let's do the square root of 6 together. Clear this out. The square root of 6, enter. And that's going to be equal to 2.44948973. Now again, I want you to keep in mind, okay, I'm not in any way claiming, nor is the calculator, that the decimal just terminates there. It actually continues to go on and on and on and on, all right? It's just that, again, the calculator screen is finite in width and just simply stops. Okay, so what I'd like you to do is also do that for the square root of 15 and the square root of 50. All right, let's do it. So the square root of 15, all right, that's going to be 3.8729833346, and the square root of 50. And that's going to be 7.0710678112. All right. Now, anyone can do that. Let's take a look at letter D. Do any of these appear to have repeating decimal patterns? What does this tell you? All right, so pause the video now and answer both of those questions. Now, I just want to be very clear about repeating decimal patterns. Now, you probably already understand this, but just to be clear, I've got a 4 that repeats here. But that's not a repeating decimal pattern. A repeating decimal pattern would have been if it was like 0.449449449449, right? Same thing here with the double 3s, right? I mean, if it had been 3.872983333333333333, yeah, repeating decimal pattern there. Same thing here, except there's absolutely nothing that particularly repeats there. So the answer, by the way, on this, the first question, is no, right? None of the 3 can we actually see a repeating nor terminating decimal pattern. So what does this tell you? Well, any number that's rational will have a repeating or terminating decimal pattern. These do not, so these are not rational numbers. These are not rational numbers. Every number that you've ever seen so far has been a rational number, even those negative things, right? And especially those fraction thingies, right? Because they literally are ratios of integers. All right, every number you've seen, with the exception of one, and we'll talk about that one in just a moment, but every number that you've seen so far in your entire mathematical career has been a rational number, but not these things. These are not rational. And we have a name for numbers that are not rational. They're called irrational. All right, now, we typically reserve the word irrational for people that aren't behaving in a way that makes any sense. Man, that was irrational of you to do, okay? Because a rational action is one that makes sense and an irrational action is one that doesn't. In terms of numbers, right, they kind of are the same thing. An irrational number is simply a number that isn't rational. That's it. Irrational numbers are those numbers that cannot be written as fractions with integer numerators and denominators. They have decimals that do not terminate or repeat. Square roots of non-perfect squares are irrational. So like the square root of 2, the square root of 10, the square root of 15. Okay? And you've seen one other irrational number. We just didn't use that term at the time, and that was the number pi. right? The number that gets wrapped up in calculating both the circumference and the area of a circle. Vaguely remember that from Math 7, right? Don't worry, we're going to review that eventually in Math 8. But, right, the number pi is an irrational number, and so is the square root of 10, because 10's not a perfect square. So let's actually kind of take a look at those two irrational numbers. Exercise number 5. For the irrational numbers pi and the square root of 10, do the following. Letter A, use your calculator to write out the value of both. Write out every decimal place. Awesome. Well, hopefully you won't need my help on this. Pause the video now, write down every decimal place that your calculator gives you for pi by finding the pi button. That's not bad anyway, we're going to need it in a few units. And then find out every decimal place for the square root of 10. Now remember, I'm not asking you for the square root of pi, like literally find the pi button, punch it, hit enter, and write down all the decimal places. It should start with 3.14 as a little hint. And then also find the square root of 10. Pause the video now. All right, well, let's first review where that pi button is, right? At least on my calculator, nicely enough, the pi button is right here, right? So it's right above my exponent button, so I'm just going to clear out my calculator so I only see the pi button, type in pi, hit enter, and its value, at least accurate to the decimal places that the calculator is going to give me, is 3.141592654. And again, notice absolutely no repetition there in terms of like no repeating pattern. Again, it does not terminate at that 4. It goes on forever without any pattern. It's really cool. There's some people that make a sport out of memorizing the digits of pi. I have no idea why. But then again, why do we do almost anything like that? All right, let's figure out the square root of 10. Now, what's kind of cool is I chose these two for a specific reason. The square root of 10 is actually fairly close to the value of pi. It's 3.16227766. Now again, be careful. This looks tempting to be like, oh, look, there's a repeating decimal pattern, but there isn't. You know, I mean, if it was 3.16222222222222, you betcha, right? But the fact that you've got 2 2s, 2 7s, 2 6s, that's not a repeating pattern, right? I mean, if it is, what would the next 2 digits be? Right? Think about that. Anyway, whatever. Let's take a look at letter B. Which number is greater, pi or the square root of 10? Justify. All right, well, pause the video. Which one's bigger? Well, it's really easy, right? Whenever you're comparing two numbers that have the same, that are written in decimal form, right? First I look at the 3's, they're the same. Then I look at the 1's, they're the same. Then this one's a 4 and this one's a 6, and the deal is over. Square root of 10's bigger, right? Square root of 10. And if we're asked to justify, I could say because 3.16 is greater than 3.14. None of the other stuff really matters at that point, right? None of this is going to make up for the fact that that 4 isn't bigger than the 6, right? It's basically that simple. Now, I point this out because a lot of times with irrational numbers, it's hard to get kind of a feeling for what their value is because this decimal goes on forever without repeating or terminating. I can't write it as a fraction, right? That's the whole point of irrational numbers. I cannot write them as a fraction. You know, pi is 3.141592, etc. I will never be able to say to you, well, actually, the value of pi is 22 sevenths. You know, or the square root of 10 is, 21 thirds. Actually, 21 thirds is 7, so it's definitely not equal to that. But you see my point. We cannot write these types of numbers as fractions that involve whole numbers. That's what an irrational number is. It just can't be written that way. So, let's keep going with this idea. Now, there's one final consideration that comes with square roots, all right? And this can lead to a lot of confusion for future courses, okay? So let's talk about this a little bit. And it's all based on the fact that a negative times a negative results in a positive, all right? Now you know that, right? So -5 times -4 is +20, or -2 times -8 is +16, right? A negative times a negative is a positive. So let's take a look at exercise number 6. Consider the equation x squared equals 100. Letter A. Represent a solution to this equation using a square root, then evaluate the square root. All right, well think about this, right? Every time we have ever solved an equation, and this is the first time we have ever solved an equation that looks like this. Every time we have ever solved an equation, what we've done is literally we've done the inverse to both sides of this equation of whatever was done to the variable. So in this case, the variable was squared, and we got 100. To undo the squaring, what we're going to do is take the square root of both sides. So x must be the square root of 100, and as we know, the square root of 100 is 10. Now, by the way, remember, you don't have to take my word for it, okay? Anytime, I could have given you this value and said, is x equals 10 a solution to this equation? And you would have taken 10 and you would have put it up in this equation, and you would have said, is 10 squared equal to 100? Right? And you would have said, well, 10 times 10 is 100. Yes, x equals 10 is a solution to this equation, right? But the nice thing now is that we actually have an operation that will undo the squaring, and that's the square root. So letter B. There is a negative solution to this equation. What is it? Justify. So there's actually a negative number that also, when substituted into this equation, would be a solution. Pause the video now and think about what that number would be. Well, that's x equals negative 10. Right? And this must also be a solution because negative 10 times negative 10 is 100. A negative times a negative is a positive. Now that doesn't pop out when we do this, right? Because I took the square root of both sides and I just got x, and that was the square root of 100, right? And clearly, by the way, I get x here because if I'm taking the square root of x squared and I ask myself, what do I have to multiply by itself to get x squared? That better be x, right? Just think about what the square root tells you, okay? But we don't get that negative 10. And that's because there's no way for the square root to really kind of know that. But what I should know is that when I multiply a negative by a negative, I'm going to get a positive. Now, at the end of the day, what that means is that when we're solving an equation that kind of looks like this, a variable squared equals a number, then I will always get two answers. One of them positive, just given by the square root, and one of them the negative version of that positive number. Let's take a look at that in one last exercise. All right, here we go. Exercise number 7. Find the solutions to each equation. Show the two solutions first as positive and negative square roots, and then as integers. The first is done as an example. All right, so let's take a look at that example. Here I've got the x squared is equal to 49. I'm trying to look for all the numbers, right? When I solve this equation, think about this. I'm trying to find all the numbers that when I multiply them by themselves, they give me 49. Well, one of those is going to be the positive square root of 49, and that's 7. And one of them is going to be the negative square root of 49, and that's negative 7. And that's it. And again, make sure you get it. 7 times 7 is 49, so it's a solution to this equation. Negative 7 times negative 7 is 49, so it's a solution to this equation. I'd like you to pause the video now and see if you can solve these two equations. Both of them will have two solutions. All right, so let's do it. In this case, one solution will be the square root of 121, and the other solution will be negative square root of 121. The square root of 121 is 11, and the negative square root of 121 will be negative 11. And again, you don't have to take my word for it. Take both of these values, plug them up into the equation. They make the equation true, and therefore, they are solutions to the equation. Never ever forget that about equations. When you're finding solutions to equations, you're looking for the values that make the equation true. And both of these numbers when substituted in for t in this equation and then squared, will give me positive 121. In this case, I've got n squared equals 25, so one solution will be the square root of 25, and that's 5. And the other one will be the negative square root of 25, and that'll be negative 5. All right. By the way, it's kind of cool, right? If I have a variable just raised to the first power, then the most solutions that that equation can have is 1. But if I have a variable raised to the second power, the number of solutions to that equation is typically 2. I bet you might even be able to extend this and say if I have a variable raised to the third power, in all likelihood, I'll have 3 solutions. Fourth power, 4 solutions. But that takes more advanced algebra. Let's wrap it up. Now we saw a lot of different things today, I'll be honest with you, right? This was a real mishmash day with square roots. We started by just looking at how square roots can show up in calculations and how you can do a calculation that's got a square root in them, especially when those square roots work out nicely, right? When there's a perfect square underneath that square root. Now another thing that we looked at was the fact that if the number underneath the square root is not a perfect square, and there aren't very many perfect squares, 1, 4, 9, 16, 25, 49, those are perfect squares. Those are numbers that have nice square roots, okay? But if the number's not a perfect square, like 10, 15, 27, things like that, then the square root of that number is an irrational number. It's got a decimal that goes on forever without ever repeating or terminating, right? The only other irrational number that you're expected to know, besides square roots of non-perfect squares, is the number pi. You'll see other irrational numbers as you move forward in math, but it's actually going to take a few years before you get introduced to any of them. The final thing that we saw is that when we're solving an equation that basically looks like the variable squared equals a number, there will always be 2 solutions to that equation. One of them is the positive square root of the number, and one of them is the negative square root of the number. Okay? You'll get plenty of practice on that in the homework. In the next lesson, we're going to look at cubed roots. For now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.